Welcome to The Explainer. Today, we're unlocking the secrets of a very specific and, honestly, a very exclusive VIP club in the world of chemistry. We're talking about bases and alkalis. Now, have you ever wondered what exactly connects the slippery feel of a bar of soap, the intense grease-busting power of Drain-On Blocker, and the fizzy reaction of baking soda? Well, today, we're going to demystify these household staples by diving into the hard chemistry behind them. Get ready, because we're going to master the core concepts, the chemical reactions, and the absolute crucial distinctions you need to ace this topic.
Okay, let's dive into this. Here is our roadmap for today. We'll start with meet the bases, then move to bases versus alkalis, cover the properties of alkalis, break down the neutralization reaction, check out the ammonium salt reaction, and finally, do a quick wrapping up.
All right, Section 1, meet the bases. Let's get right into it. To really wrap our heads around this chemistry, we need to anchor it in the real world first. So what do soap, drain cleaner, and baking soda actually have in common? I want you to think about the physical sensation of washing your hands. You know, that slippery, soapy feel, right? Or think about the heavy-duty chemical power it takes to dissolve thick grease in a clogged drain. These items seem totally different in our everyday lives, but chemically speaking, they belong to the exact same family.
The secret ingredient that both thick, germ-killing bleach and your everyday toothpaste share is they are all bases. But there's a massive range in how strong they are. Strong bases, like the ones in bleach or drain cleaner, are incredibly powerful. I mean, they can literally dissolve grease and protein, which is exactly why you have to handle them with extreme care so they don't react with your skin. On the flip side, though, we use weak bases every single day, completely safely, right inside our mouths when we brush our teeth.
Moving right along to Section 2, bases versus alkalis. This is a big one. Seriously, this distinction is one of the most frequently tested concepts out there. A base is broadly defined as any metal oxide or hydroxide. Basically, they contain either the oxide ion or the hydroxide ion. That's the broad category. But I want you to think of alkalis as the exclusive VIP club of bases. All alkalis are bases, absolutely, but only the special bases that possess the superpower to actually dissolve in water get to be called alkalis. Solubility is the absolute key difference here.
Now, what's really interesting about this VIP club is how they behave. Alkalis are soluble bases that produce hydroxide ions, that's OH-, when they dissolve in aqueous solutions. And the difference in their strength all comes down to ionization. Strong alkalis, like sodium hydroxide, become fully ionized in water. But weak alkalis, like aqueous ammonia, which, fun fact, unusually doesn't even contain a metal ion, are only partially ionized. Let's keep the momentum going with Section 3, properties of alkalis. Time to build your mental checklist.
If you were to taste a safe, weak alkali, you would immediately notice a really bitter taste. They also have that characteristic slippery, soapy feel, which is literally what you're feeling when you're washing your hands with soap. Chemically, they always register a pH value greater than 7. And here's the cool part. Because they produce ions in water, these solutions actually conduct electricity. Finally, the classic laboratory test. Alkalis will always turn red litmus paper blue. Now, chemists visualize these properties using indicators, which are basically colored dyes that change color when added to an acid or an alkali. When you dip red litmus paper into an alkaline solution and it turns blue, that color change is the definitive, successful test. It's the ultimate signal proving the presence of those hydroxide ions. But hey, color is just one way to measure this. A digital pH meter helps us determine relative alkalinity with serious precision. A strong alkali, like the sodium hydroxide we talked about earlier, will have a very high pH, somewhere up around 10 to 14. A weaker alkali, like ammonia or baking soda, will sit lower down on the alkaline side of the scale, usually between a pH of 7 and 10. All right, Section 4, the neutralization reaction. This is where things get really dynamic. This right here is the fundamental equation you absolutely need to memorize. Base plus acid reacts to form salt plus water. Think of it like a recipe. If you take a base, say copper oxide, and react it with an acid, like dilute sulfuric acid, you get a salt, in this case copper sulfate and water. The crucial thing to drill into your memory for your exams is that salt and water are the only products of this specific reaction, nothing else.
To really understand why this happens, we have to strip away all the spectator ions and just look at the core ionic equation. H plus OH minus reacts to form H2O.
So the crucial point is that the hydrogen ions from the acid and the hydroxide ions from the alkali find each other, rearrange themselves, and form completely neutral liquid water. This is the absolute core mechanism of any neutralization reaction. It's kind of beautiful when you think about it.
Next up, Section 5, the ammonium salt reaction, a very specific, very important requirement to know.
Here is the step-by-step recipe for this one. Step 1, you mix an alkali with an ammonium salt. Step 2, and this is highly important, do not forget this, you must apply heat to the mixture. When you heat an alkali with an ammonium salt, a special reaction occurs. The products are a salt, water, and crucially, ammonia gas is given off. So the rhythmic word equation to remember is alkali plus ammonium salt produces salt plus water plus ammonia.
Now, you might be wondering, how do you actually prove that the invisible gas floating away is ammonia? Well, you test for it. And ammonia has two massive, undeniable giveaways. First, it has an incredibly sharp, characteristic pungent smell. Believe me, it hits your nose hard. Second, because ammonia gas is actually a weak alkali itself, if you hold a piece of damp red litmus paper in the gas, it'll turn blue. The paper must be damp, though, so the gas can dissolve and form those hydroxide ions to trigger the color change.
Let's move to Section 6 and see how this all builds together in wrapping up. Let's do a quick high-energy summary of our chemical rivals, acids and alkalis. It really boils down to this. Acids produce hydrogen ions in water, while alkalis produce hydroxide ions. For the litmus test, acids turn blue litmus red, whereas alkalis turn red litmus blue. And finally, looking at the pH scale, acids sit below 7, while our alkalis rule the top half, sitting proudly above 7. To leave you with something to chew on, let's apply all this to the real world. Imagine a farmer discovers their crop's soil has become way too acidic to grow food. Based on the neutralization reactions we just learned, how could they use a cheap, readily available alkali, like calcium hydroxide, to save their crops? Think about the ions interacting in that damp soil. I hope this explainer has given you the chemical tools to easily solve puzzles exactly like that one. Thanks for joining me in unlocking the VIP club of bases and alkalis. Catch you next time.